Alright, so in this video I'm gonna be explaining another approach for domain adaptation, still in unsupervised setting, and it is source free without source data because sometimes we have privacy issues, so we cannot share data, but companies can share models. They don't need to share data because of privacy issues. So I'm gonna be explaining this paper in 2020. Model adaptation, unsupervised domain adaptation without source data. It means it is source free. So we investigated challenging unsupervised domain adaptation setting, unsupervised model adaptation, and we aim to explore how to rely only on labeled target data to improve performance of an existing source prediction model on the target domain, since labeled source data may not be available in some real-world scenarios due to data privacy issues. For this purpose, we propose a new framework which is referred to as collaborative class conditional generative adversarial net to bypass the dependence on the source data. Specifically, the prediction model is to be improved through generated target style data, which provides more accurate guidance for the generator. As a result, the generator and the prediction model can collaborate with each other without source data. Furthermore, due to the lack of supervision from source data, we propose a weight constraint that encourages similarity to the source model. A clustering-based regularization is also introduced to produce more discriminative features in the target domain. So this is the comparison between conventional data-based adaptation, which is the left side. This is the conventional. And our model adaptation. This is the proposed model in this paper. But conventional unsupervised domain adaptation requires labeled source data, while our proposed model adaptation method only relies on unlabeled target data. So it doesn't even use source data. This is very interesting. It doesn't use the labels of source data. It only uses the target data. So we consider a novel and challenging adaptation setting which aims to transfer a prediction model across different domains with only unlabeled data. This is not feasible for the existing adaptation approaches. To avoid relying on source data, we propose 3C GAN, where the generator and the prediction model can be collaboratively enhanced during adaptation. We demonstrate that the proposed model is sufficiently effective on multiple domain adaptation benchmarks and outperforms recent state-of-the-art results in the absence of source data. So we elaborate our model for unsupervised domain adaptation problem where we merely have access to a pre-trained prediction model from the source domain and unlabeled target dataset. So our goal is to adapt this model prediction C to the target domain. To this end, we propose a collaborative class conditional for model adaptation in the presence of source data, except for existing pre-trained that prediction model, this pre-trained classifier, this prediction model C. Our framework consists of another two components. We have a discriminator for matching target distribution and generator condition on randomly sampled label for producing valid target style training samples. By incorporating the generated data during training, the performance of C is improved on the target domain, which can in turn promote the generation process of G. So this is the target generation, and this is the model adaptation. So in target generation, because during target generation, we aim to learn a class condition generator for producing target style training samples. Via the discriminator D, this is the discriminator, and the prediction model C. This is the prediction model C, which is fixed as denoted by the dashed line. The generated images and proposed regularization are used for model adaptation, and these two procedures are repeated with generator and the prediction collaborating with each other. So you see we have noise because we can even generate those images. We have generator, but this generator is interesting because it is collaborating with one thing that pre-trained prediction model C. It is collaborating. It has collaboration with that as well, so that we have these synthetic images, and here we have the target. So the discriminator allows us, because we have adversarial loss, allows us to have the target generation. So to avoid using source data for domain adaptation, we propose this model. The objective can be expressed as this loss, which you are familiar. G is updated to fool the discriminator D. So this generator fools this discriminator D with a similar distribution as X sub T. So the adversarial loss can be written as expectation of D times 1 minus G of Y. Although the adversarial simulates the target distribution, it cannot guarantee the semantic similarity due to input label Y. Inspired by this reference, we propose semantic similarity loss based on the existing prediction model. It enforces the semantic similarity between X sub G and the input label Y based on prediction model C. So this is the semantic similarity loss. Now, P theta indicates the class probability predicted by a prediction model. And this loss enables the generation semantics. After including this adversarial loss here that matches the target distribution, now we have a combination of these losses, both semantic similarity and adversarial. So this hyperparameter lambda is a trade-off between these two worlds. We alternatively update the discriminator D and generator G for optimizing this equation 1. As a result, G can produce a new target style instances, which are used to improve performance of C on the target domain. C and G collaborate with each other during training, since the enhanced C can provide more accurate guidance for G, and a more reliable generation can in turn improve performance of C. Therefore, the overall framework refers to collaborative class conditional generative adversarial network. So in addition to generator, we further include this regularization, we have two regularization to enhance the performance of our prediction model. The final optimization is just a trade-off between these three. So we have three hyperparameters. They adjust relative effects of each loss. But note that during adaptation, the source dataset is not used. And we have weight regularization. This weight regularization that can be written like this. Theta phi is just parameters of pre-trained on the source domain, which is fixed. We can observe that if theta sub cs is set to 0, L will be reduced to standard weight decaying regularization. So this allows us not to change too much. It prevents the adapted model from changing too significantly. On the other hand, the enforcing adapted model similar to the source model can be regarded as preserving the source knowledge. This always reminds me one thing. In continual learning, we don't want to change the parameters each time we have something new. So it's a trade-off between rigidity and flexibility. Plasticity. I remember plasticity stability dilemma in neuroscience. So clustering-based regularization. Most domain adaptation methods focus on adaptation process where the unlabeled real target data are only used to estimate the target distribution, while we consider that unlabeled target data can be used to explore the discriminative information on the target domain. The cluster assumption implies that the decision boundaries of the prediction model should not go through data regions with high density. Therefore, we minimize the conditional entropy of the predicted probability on the target domain. So I've seen this several times in different papers. So interesting that everybody is using this entropy. However, as pointed out, the conditional entropy derived in this equation is not reliable when the prediction model is not locally smooth. So to improve the approximation of conditional entropy on unlabeled data, a local smoothness constraint should be added, which is defined as this maximum of KL divergence between these two distributions. Of course, this constraint forces the prediction output to be similar between x sub t and x sub t plus r, because we have perturbation r that affects the prediction most within an intensity range of c. Therefore, the final clustering-based regularization is formulated like this. So we also add the KL divergence between that distribution and the perturbed one. So this is a pseudocode for the adaptation. We randomly sample and random vector from uniform distribution. So here we generate new samples. The generator, the update, this is the discriminator, the adversarial part. If we start in adaptation, then we use this. So we update the prediction model, discrimination, generation to optimize the objectives. So for each task, we only use source data to obtain the pre-trained source model, and it is not used during adaptation. So for experimental, they use digit and sign data sets The Office 31 is very popular. This one is also used, is a challenging dataset for domain adaptation from synthetic domain to real domain with 12 shared classes. And the synthetic domain contains around 152,000 images produced by rendering 3D models under different conditions. So if you go from different source to different target, you have these very high classification accuracy. But classification accuracy of Office 31 on ResNet is, for example, from this source to this target is a little bit lower.